Mark William is a William Pina Professor of Information Management at the Department of Architecture at Texas A&M University. Professor CLAYTON has been a faculty member at Texas A&M since 1995. He has served the College of Architecture as Executive Associate Dean and the Department of Architecture as interim head. He was also past president of ACADIA and founding member of ASCAAD. Professor Mark CLAYTON, the floor is yours.
I'm extremely pleased to be here, and they got the updates installed just in time. So I hope I'm not. So my own involvement with the Arab Society of Computer-Aided Architectural Design goes back a long way. I am a founding member of the organization and was invited by Dr. Jamal Al-Khwarizmi to give a keynote speech at the first conference. He had finished his PhD at Texas A&M and actually gave me my first opportunity to be a chair of a PhD committee. So it was a real pleasure to work with him back then. His dissertation, completed in 1999, was prescient for our current time of pandemic. It was a study of computer-mediated architectural design, and it explored how to use net meeting as a platform for working together without being in the same place. I remain impressed with his insight, discipline, and rigor. I also thank Mustafa Debbieh for suggesting that I give this keynote address. I am honored to share my thoughts with you. I was asked to speak about information management. And this seems an appropriate topic as I hold the William M. Pena Professor of Information Management in Architecture. But I don't really think of my activities as information management, but instead I see them as transforming information into knowledge. Knowledge is distilled, abstracted, and actionable. Like the ancient library at Alexandria, the cloud contains all knowledge of our culture. In these times, learning about architecture is inextricably learning through computing, CAD software. By learning through CAD software, BIM software, graphic software, energy analysis, structural analysis tools, we learn architecture. Even aesthetic theory can be learned by finding and applying algorithms and data structures. That is the philosophy behind the BIM Sim Lab, founded at Texas A&M by myself and Dr. Wei Yan. Our focus has been upon building information modeling and building simulation. Our field of inquiry is architecture in all of its manifestations and varied definitions, whether the science or art, the scale of a table setting or a city. We see our investigations producing prototypes, test beds, and principles that other researchers and even practitioners can use. In reflecting over the last decade and a half of the lab, for this keynote, I decided to present several dissertation projects and organize them into 4 categories. The categories are not comprehensive or exclusive. We do other things too. But these investigations still amaze and thrill me with their ambition and intellectual depth. First is the category of design process. We live in a post-digital age. And what that means is that the qualifier digital doesn't really mean much anymore. Everything is digital. And I see that as design must inevitably change to accommodate this new reality we have. The second category is physics performance. So topics such as energy simulation have long been of interest in researchers in architectural computing, but their breakthroughs in cloud computing and neural networks that have made some of the intractable problems, previously intractable problems, now doable. The third category is an emerging one. Using massive computing resources and probabilistic analysis, we can now study and simulate how people react to their environments. Architecture can be used to encourage behaviors in people. Now we can model that phenomenology of architecture. And the final category is aesthetics. Many architects and researchers avoid claims about aesthetics. The aphorism, beauty is in the eye of the beholder, dissuades them from considering aesthetics, thinking it's too arbitrary. But aesthetics is not about beauty, but about systems of beauty, about whatever may be universal or at least widespread in affecting people to have an experience of beauty. Aesthetics is a crucial topic in architectural studies, and I believe it can also be represented in this great universal library that we call the internet. So first, to tackle this this point of design process, I'd like to talk about a couple of research projects that have tackled ideas in design process quite directly. The first one I'll mention is a work by Ozan Ozener that he completed in 2009, where we posited that studio education for integrated practice should be dramatically changed by the advent of building information modeling. Limitations of historical design process include its reliance on tacit knowledge and reliance upon abstract solutions. So at the very early stages of design, most of the writings on design process kind of walk one through a concept development stage where one draws heavily upon tacit knowledge to come up with an abstract design solution, and then that solution is refined and enhanced throughout a long process. This has some problems. One is that tacit knowledge is great when you have an expert, but not so good when it's not an expert. And two, that it makes simulation very difficult because the model is not complete. So Dr. Ozener turned the process on its head, and in his Studio 21 method, the 21 stands for the 21st century, the first step is to produce a base case design rather than a concept. The base case could be a precedent or existing building, or it could be a quick response that lacks much subtlety or thoughtfulness. But the key issue here is the representation is high quality, making it possible to conduct cost control, energy simulations, structural calculations, and so on. So the base case is a full building information model that sets out the issues and standards for the project without trying to tackle design issues yet. So building the base case is difficult and time consuming. And not only does it require designing a building with a high level of detail, it requires integrating the analytical and simulation tools that support decisions. But once it is built, the design process becomes fun, exciting, and fast. So once the base case is built, the designer has a project BIM that enables rapid production of various schemes. So this is a special instance of BIM that is tailored to the particular project. And rather than hoping that the initial concept is right and then devoting months of time and expense, the designer can collect evidence for the performance of each design option. The designer can make use of the same BIM after that project BIM is created to run simulations of each alternative. And design decisions are now based on comparison of evidence rather than a hunch. So, so the base case allows one an iteration to steer the design iterations, and so that the last iteration is better than the first, is clearly better, documented better than the first. So, so Dr. Ozener tested this idea with a design assignment with graduate students. The students were surveyed and interviewed to provide comments. He got great feedback from it, and the method, although different from their custom design methods, it could be taught and adopted. The positive delta in performance from the base case to the ultimate design helps make a case for the value provided by the architect. The basic theme and idea has been the basis for continuing methods explorations at the BIM-SIM group. The second dissertation I would like to talk about was conducted by Dr. Ramani Asal under the supervision of Dr. Wei Yan. He integrated an optimization framework into Autodesk Revit to support feeding simulation output from numerous tools to aid the designer in choosing the optimum solution. Rather than use the more common weighted average approach, he used the Pareto optimal approach. The Pareto front is the edge of an imaginary space in which the performance for each criteria is plotted such that moving off the edge will reduce the performance with respect to one or more criteria. Arguably, being on the Pareto front is the most optimal solution, as all criteria are achieving a maximum performance. Now, the next kind of general topic in our lab's research is the idea of physics performance. So much of the technical building performance is simply the response of the building to physics: gravity, thermal environment, air movement, water movement, etc. BIM changed our computer simulations by allowing them to be tightly integrated into a multi-criteria optimization environment conducted by architects. Parallel processing has integrated has changed the possibilities again by crunching massive data sets to derive insights. Ever smaller slices of space and time lead to increasing accuracy and sensitivity, but ever larger demands on computer resources. A new pattern for research in the BIM-SIM lab is to use massive cloud computing resources to generate very large amounts of data. This data can then be used in machine learning to devise neural networks to accelerate a simulation and make it effective within the rapid timeframes of the design process. So the first one I'd like to bring up is a model for performance evaluation of climate adaptive building envelopes developed by Hyun-Sub Kim and completed in 2017. So he took on a highly ambitious problem of how to simulate the performance of a dynamic facade. More buildings are being designed to have shading devices and light control systems that move in response to changing solar angles and solar intensity, but that presents great difficulty in simulating them and designing them for that performance that they intend to achieve. So the quantity of calculations can become staggering. In Dr. Kim's investigation, he posited a need to optimize the dynamic facade for thermal protection and lighting quality. The dynamic facade could have dozens of different states, and the solar angles change continuously throughout the year. The weather patterns can change from year to year, or the climate patterns can change from year to year, weather day to day. And so this required a very large numbers of computing. So his solution made use of cloud computing to perform thousands of runs using Energy Plus to find the best possible schedule for operating the facade devices. The performance resulting from each position of every facade element was computed to enable an exhaustive search of elements for that schedule. And the thermal performance and lighting performance under the various operational schedules were computed to find the Pareto optimal solutions. Dr. Kim further compared his methods to other methods proposed for simulating movable facades. He presented convincing evidence that his method achieved more accurate results that apply to a wider range of potential designs. A second project was conducted by Rania Labib and finished in 2019. And she pointed out that optimal performance for a building should consider not merely the subject building, but multiple buildings in a district. And her concept is an extension of the notion of an Internet of Things, and she called it a facade Internet of Things. Many small smart devices can collaborate to solve problems or execute tasks that are beyond the ability of one task. So, for example, lighting in one building could be harmed by the reflectivity of the facade of another building, creating glare or other kinds of discomfort. Movable window shades could also be angled to capture sunlight with building integrated photovoltaics. So once again, she set up a optimization problem between the glare, the daylighting quality in the rooms, and the production of electricity. Her solution was to posit a radio frequency network, such as a Wi-Fi network, that could enable two or more buildings to act as agents and negotiate with each other to determine optimal use of dynamic facades and a facade's Internet of Things. The simulations show that coordinating manipulation of the shading devices of the two buildings could reduce that by coordinating the manipulation of the shading devices, she could reduce glare and increase daylighting performance while maintaining the energy production. The investigation required thousands of simulations. Her estimates are that with desktop computing, simulating one scenario would require a year of processing time. Instead, her solution was to enlist a high-performance computing environment to for massively parallel calculations. She used the extreme science and engineering discovery environment to field 1,000 single-core nodes and cut processing down to 3 hours. So she used a similar process for the photovoltaic simulation. And then developed used cloud computing resources and neural networks to allow her to produce results very fast. The investigation gave strong evidence for the hypothesis that an FIOT could improve the performance of a neighborhood of buildings but it also demonstrated cloud resources and neural networks can be marshaled by architects to make formerly impossible tasks now tractable. Now, if I switch now to the phenomenological performance, there are a couple of exciting dissertations that I'd like to share with you. One of them was conducted by Saeed Zarenmeir in 2016. And architecture inevitably is embedded in phenomenology and how the human responds to architecture. Dr. Saeed Zarenmeir arrived at Texas A&M with an interest in aesthetics. Is there something about the form and ornament of a building that makes it attractive? Professor Jeffrey Booth presented an argument that real estate profit derives from repeat customers who enjoy the experience of being in a place so much that they come back. The interaction of these interests and insights led to study of the computer science topics of crowd simulation and pedestrian dynamics. So Dr. Zarenmeir took on a purely model-based approach that we did not have available the enormous samples that would be needed for an empirical approach. So he conducted a thorough study of literature to figure out what everyone had written about pedestrian dynamics and built a digital model to handle that. So so basically, there's an agent that models a pedestrian. Let me see if I can back this up. And placing the agent on a location establishes a starting point. The location and goal initiates a search path for a path, a search for a path. And the architectural setting is sliced up into a planar grid to allow study of each step. Locations on the grid are coded as either attractive or unattractive or neutral. For example, a facade or fountain could be noted as attractive, while a busy road or garbage collection site would be noted as unattractive. In his system, the physiological state of the agent is also incorporated. Is the agent hungry? Is the agent tired? Is the agent dissuaded by a steep climb or encouraged by one? Does the agent have a personality that resists change of goals, or does it easily adjust goals? So these are all different kinds of pedestrian behavior that one would see. So at any one location, the algorithm assesses the next option. An isovis is calculated to detect whether attractive or unattractive places are visible. The shadow pattern is noted to modify the choice of path by thermal comfort. An optimization module resolves choice of path based on other numerous factors. With each step, the calculations are repeated with the new isovis, the new thermal comfort, the newly emerged goals, and the new agent state. The resulting model of pedestrian behavior seemed comprehensive, but he added an additional factor. Common sense suggests that impulse and random choices are also important. So in his final step, he implemented a random factor in a Monte Carlo simulation of thousands of pedestrians to enable the simulation to trend toward the most likely path. The study was not validated against empirical data. However, the weighting factors of the algorithm are tunable. If such data becomes available, a next step in validation would be to tune the software to replicate the observed behavior. His work is a bit of a surrogate or a way of looking at architectural aesthetics. So the idea was to build a apparatus by which one could study architectural aesthetics by observing how people move through space, what attracts them, and start to get a phenomenological notion of aesthetics. Now, the second phenomenological project that I'd like to talk about was just completed by Dr. Won-Jae Yu, and he took on the task of modeling outdoor thermal comfort. The Texas A&M happens to have a world-renowned scholar, Dr. Robert Brown, who has devised a calculation procedure for outdoor thermal comfort. So we took that and implemented it as a add-in to Autodesk Revit to help try to help designers get evidence for their designs of outdoor thermal comfort. So he used a model-based research method derived from the well-established COMFA algorithm by Dr. Robert Brown. The modeling strategy, again, was to divide the urban space into square cells and calculate the thermal comfort of each cell. To enable the user to trade speed of execution against precision of results, the granularity is adjustable. To work as an aid to designers, execution speed is very important. The decision to place a tree or fountain or grass-covered lawn at one location or another will affect the thermal comfort of an area. The designer wants feedback immediately while juggling the many options and the many competing criteria to optimize. Dr. Yu accelerated the algorithm using several techniques. To calculate surface temperatures, he used deep learning based on massive data sets calculated with Energy Plus. He calculated all possible solar incident angles to train another neural network to provide angles rapidly. He implemented an outdoor thermal comfort model trained from big data calculated using the COMFA model. So once again, by using synthetic big data, he was able to train neural networks to provide an extremely fast execution. So the execution time in seconds or minutes allows the designer not only to study comfort at a particular instance, but to look at the probabilistic and statistical comfort of a space over a much longer period of time. Now, the final dissertation I want to tell you about is one of my favorites. It was conducted by Nancy Al-Assaf of the University of Jordan. It directly tackled the idea of aesthetics. Her driving goal was largely educational. Can students be taught the idea of architecture as a language to enable them to make consistent decisions with consistent aesthetic consequences? And, because of the consistency of Richard Meyer's aesthetic expression throughout his career, and Dr. Al-Assaf's expertise in the language of Richard Meyer, which she had studied for her master's project, she undertook an action research method to show that the language could be formulated as an algorithm that could be taught to students. So her analysis of Meyer's language dissects examples of Meyer's houses into a handful of concepts. There are two axes, two orthogonal axes to define a grand process and a transverse axis. The living spaces are arranged into two rectangular volumes, one private and one public, designated by one of them closed off and one of them largely edged with glass curtain walls. There's solids and voids that are subtracted from it. And then overall, there is a vocabulary of elements that are used over and over again in every one of his house designs. So she demonstrated the correctness of her implementation of the language by showing that many of Meyer's house designs could be rapidly modeled by following the algorithm. She didn't necessarily represent the entire algorithm in the computer, but was able to specify the algorithm so that a person could follow it. Now, the next step, but I didn't let her stop there. The next step was to move beyond reliance upon a skilled user by automating as much as possible. So she built relations among the various parts by locking elements to alignments, parameterizing masses, placing walls and doors and faces, and writing dynamo scripts to implement or automate some additional ones. She even automated the layout of the houses and presentation of them with standard views, view templates, and sheet layouts. Now, the next kind of question is could not only she do this, but could she teach it to people? And, I pushed her even harder and said, well, maybe you can teach it to people, but can anybody else teach it to people? So we enlisted another instructor, and we taught 48 sophomore students how to use her system. So their first assignment was to take Meyer's language and build more Richard Meyer houses. They had to create 4 houses apiece. So here you're seeing the houses they created. And some of them are more successful and some of them are less successful, but they all do have a flavor of Richard Meyer. And I haven't done the study to show them necessarily to an architectural historian and ask them if it's a Richard Meyer house. Well, actually, we have done that study, but we'll get to that in a moment. So, but that wasn't enough. That she wanted to study whether whether the students learned something about languages and could create their own architectural language and implement multiple versions of it. So these are the languages that each student created. They each created 4 houses within their language. And some of them are very Richard Meyer-like. That one was actually a Gwathmey Siegel clone. And some of them, the students wanted to deviate a lot more from the Richard Meyer language, but they still created a language. So, so this showed that they had learned something about the notion of architectural language so that they could use that in their own design. Now, even that wasn't enough. And we wanted to sort of get a sense of an independent evaluation and validation of this process. That if I said it was good and she said it was good, well, we could be suffering from confirmation bias, and we just think everything we do is good. So we brought in 3 outside experts to look at what she had done. And we had 400 houses designed by the students. We brought these 3 guests in for 2 days. We paid them a small stipend to be there, and they reviewed all of the projects. They explored what she had done, discussed it, and they agreed that her claims were valid. The Meyer language had been captured as an architectural information model and could be taught to students. The students not only learned how to be tool users, but learned the notion of architectural language in general. And they were able to produce new languages. So, so I think, a basic sort of contribution of this and implication is that Autodesk Revit and other BIM tools can be used to represent architectural theory knowledge, that they can be used in early stages of design. These students produced 400 house designs that were pretty good, really, in just a few weeks' time. Future work could look at more architectural languages, could use generative design techniques, could do performance modeling of every single one of these schemes, every scheme developed. So you could imagine a neighborhood of Richard Meyer houses that are also high performance. Now, I want to conclude with just a few speculations, a little motivation of why I'm doing this. And I see we have huge problems in the world right now, and our imperative is to rebuild a planet decimated by climate change, pressured by a population of 9 billion humans, with a contaminated environment and dwindling natural resources, all by the year 2050. That's what we're facing. And I really believe that techniques such as these of marshaling computer technology, of the metaverse, provides us some hope of success. So by adopting neural networks, cloud computing, symbolic modeling, automated representation, and documentation, maybe we can keep architecture as a discipline and profession relevant in these dire times. And I believe that architecture really is inevitably a major part of the solution. And that final aspect of looking at the aesthetics is absolutely critical, because we could solve the problem and it be incredibly ugly, or we could solve it and it would be beautiful. I hope these words have been provocative and inspiring. I invite you to contact me to continue discussions and come to Texas, visit. And I offer special thanks to the ASCAAD Organizing Committee and Professor El Bastawisi. Thank you very much.